Hi everyone, my name is Negev Shekel Nosatzki, and I'm going to talk today about how to approximate the eddy distance in near linear time up to a constant factor. That's a joint work with Alexandr Andoni. So the problem setup is as follows. We have two strings, x and y, over alphabet sigma and length n, and we would like to calculate what is the minimum number of insertion, deletions, and substitutions of characters in order to transform one string into another. For example, if we would like to check the eddy distance between banana and ananas, we would have to delete the letter B and add the letter S, so the answer is eddy distance 2. And this problem has many applications in bioinformatics, in natural language processing, and in many other problems. So computing the eddy distance is a classical dynamic programming problem. It's taught in even undergraduate classes in dynamic programming, and it's known to have a quadratic time through dynamic programming by Wagner and Fisher. So the question is, what can be done to improve the quadratic time? And there is a long line of work that was trying to do that. The first improvement was polylogarithmic 6 years later. And then there was a lot of work to try to improve it. And most of the success has been in special cases like small eddy distance, average case complexity, and many others. And it turns out that if one believes in SAS, actually you cannot get better than a quadratic time or near quadratic time in the worst case, if you would like to compute this eddy distance precisely. Then the question remains, what if we allow some approximation? And there have been a line of work there in the early 2000s. In the beginning, we were able to get some polynomial approximation. And later on, we were able to get polylogarithmic approximation in near linear time, which was work that was done in 2009 and 2010. And more recently, there was a breakthrough that allowed us to do even better approximation, a constant factor, in fact, in a subquadratic time. And in the beginning, it was a quantum time, and then in regular time. And then the question is, can we do better than subquadratic? Can we do near linear? And earlier this year, there were two papers that showed that one can get near linear time if you get a pretty large additive error, n to the 1 minus some function of epsilon, but then you can get near linear constant factor approximation. So our result shows that, in fact, you can compute constant factor of the distance in near linear time for any pair of input strings. And what is the approach? First of all, one can think of an eddy distance between two strings as an alignment, a monotone function between a set of n to another set of n, such that the alignment matches between characters of x and y. And instead of looking at characters, some of the earlier work showed that it may be useful to look at intervals, which are a substring of length w of x and y. And we can define those intervals as xi, for example, which is a substring that starts at the letter I and is of length w over x. And it's useful to think of w as roughly n to the 1 minus epsilon in our case. And the fact is that up to a constant factor, the eddy distance between x and y is roughly the sum of eddy distances of size w over all the characters I and pi of I normalized over w. So the goal becomes, let's find the near optimal alignment pi between those intervals, between intervals xi and yj, using calls to eddy distance of slightly smaller lengths. Okay, and this approach was started in 2018, and why would it help? Okay, so if one would do those naively and compute all eddy distances of length W, it would actually increase the time, right? It will take W squared time to compute the distance, and there are N squared as many, so it's N squared W squared, which is even more than quadratic. But then there are some ideas how to improve that. The first idea is just to consider i's that are multiple of some delta W's, right? So we don't look at all i's, but we look at multiples of roughly W. And now you get something that looks at least closer to the quadratic time that was originally, right? You get N squared over delta squared, but you also pay some additive error, because every time you don't look at the exact location of the alignment, you look at something close by, then you have an additive error. And now we want to get better than quadratic. So there are two ideas that are balancing itself out that was proposed in the original paper. The first one is that if one can think about interval density as the number of intervals that are close to an interval, and for simplification, let's assume they are all roughly the same, then you can actually reduce the amortized time, because if you look at one interval and compare it to many other and it's close to them, then you can say that they are those intervals that are close to some intervals to the first interval, they're also close to each other, right, up to a constant factor. So if the density is D, then you get a D improvement in the number of eddy distance recursive calls, right? And the other idea is, so this idea is very good if intervals are coming from a very dense neighborhoods. And the other idea for sparse neighborhood is that in alignment, if we have if the true pi of IW is J, then most likely pi of I plus 1W is roughly J plus W, up to a constant factor, especially in close by interval. And there we can actually get an improvement, which is N over D. And the balance between those cases, right? So the first idea 2 is very good for the dense case, and idea 3 is very good for the sparse case. And in the worst case, one can balance them out and get the number of eddy distance call is N over delta W to the 1.5 time W squared to compute such smaller eddy distance, right? And then one need to actually find the shortest path, which takes another N over W, roughly N over W squared. Okay, and actually one can improve this W squared to W to 1.5 if instead of just brute forcing all those ADW call, we're just going to recurse it for smaller and smaller W's. And so those ideas were able to get roughly N to the 1.5 time to compute constant. And earlier this year, there were two separate works that showed that you can combine the dense and the sparse case, and in order to get near linear time, because you use the advantage of both. But because first of all, you use idea 1, then you need to get an additive error there, which is a near linear additive error. And the other problem is not just idea 1, but some of the standard approaches to solve this problem allow them to ignore some fraction of matches between xi and y pi I, right? So say there is a certain fraction, roughly n to the minus some function of epsilon, then if we miss, we don't care, right? Because if we just sum them all up, it's another additive error. So in our case, we cannot use idea 1 because we don't have additive error, certainly not for parameters that we care about. Okay, and we cannot afford to ignore some matches. So here is what is our approach, how we solve this problem. Because if we would try and do the same thing over recursive call, it would be very hard. It's prohibitive because the number of recursive call will be prohibitive for us. So instead of running recursion over smaller w's, we're going to start with the smallest w, and we're going to build up. We're going to start with word size 1, and then we're going to go to word size n to the epsilon until we reach a word size n. And every time we are building a distance oracle, d sub w, for a metric, which is the size of all w intervals i's, and with the distance edw, all right? And again, the interval is all the x intervals and all the y interval that start at any single coordinate I or any single coordinate j. Right, so the first data structure is simply, we simply do hashing or we do humming over sigma, and we get a data structure that shows all the clusters of single characters of sigma. And every time we're going to build a new data structure using the previous data structure. And in the end, we're going to output what is the distance between x1 and y1. And this will approximate the distance between the entire strings, because now we're going to approximate the interval of the full length. So what would be the guarantees from the data structure? Our data structure will always return an upper bound on the eddy distance, and so the data structure will always get 2 intervals, I and j, and we will get and we'll output the distance that will always be an upper bound, and it will be a lower bound roughly. What does it mean, roughly a lower bound? It means that up to a constant and on average, and only for an optimal alignment. So if we're gonna compute as the data structure from things that are not in an optimal alignment, then we have no guarantees about what they will give us back. But as long as we're gonna query i's and j's that are part of an optimal alignment, then we will get on average the right answer. And those data structure queries will be very fast. They will take O star 1 time and to the O epsilon time. So now the new goal is, say that we have access to a data structure over a word of size W over n to the epsilon, build a new data structure over words of size W in near linear time. Okay, so that's the new goal. So how do we going to do that? How are we going to build a data structure for length W intervals using the previous data structure? And there is 2 components to our algorithm. The first one is we build an alignment distance oracle. Okay, ALW, I, and J, and this ALW oracle will have a similar guarantees like the data structure, right? But it will approximate the eddy distance of I and J on average up to a constant, and then it will also be very fast. But now it will be able to do that on word size W instead of word size n over W, and this is given access, and this is for specific I and J, right? And now say that we have access to such such a alignment distance oracle. We would like to build a graph G sub W, and this graph will have the vertices of the graph will be all the interval, right? So we have 2n vertices for the graph GW, all the x and all the y intervals. And this will be a sparse graph because we only can afford near linear time. And it will be a sparse representation for this ALW metric, right? So it will give the same guarantees as we would like to have, meaning that for all the pairs of intervals, we will have a strict upper bound on the eddy distance, and we will have a lower bound, which is bounded by this AL WIJ. distance. So we're going to build this sparse graph G, and using more standard tools of a Matusek from 96, we're going to embed such graph into L infinity norm for dimension n to the epsilon, and this will generate a new distance oracle for strings of length W. So now, how are we going to do that? How are we going to build this graph GW using the oracle call to ALW? And it turns out that it's enough to build a graph GWC for every scale C. So what would be the guarantees of this graph GWC? First of all, we're only going to add an edge to the graph GWC if the AL distance between I and J is at most constant away from C, right? So we're not going to add edges that overestimate IJ ever. And then we're also showing that for any alignment, right? Then we only care for one alignment, which is the optimal, but for any alignment pi, if the alignment distance between xi and y pi I is at most C, then we will have a two-hop pass in GWC. Again, so I will explain it. So if we cannot, because it's a sparse representation, we cannot have a one hop, we cannot put an edge between every pair of matches, but we will do the second best. We will do a two-hop pass, right? That each of those hop will be of a weight C in this graph GWC, right? And we're going to do that using near linear number of time, a near linear number of call to the AL oracle. And this AL oracle is very fast. It takes n to the epsilon time. And we're going to have some error, right? So this cannot be guaranteed for all eyes, but this is where we get the on average sync. We're going to miss some portion of matches, but the number of things that we're going to match, that we're going to miss, is a constant factor away from the number of things that were wrong to begin with, right? So if we had, let's say K, we call them corrupted matches to begin with. There were K things that are expensive between I and pi I. Then we may miss some O of K good matches, true matches, right? And the final graph GW will simply be a union of all the GWC graphs. Okay, so this is the guarantees for the GWC graphs, and GW will be the union of them. Okay, so how are we going to construct those graphs? How are we going to obtain such guarantees? And again, we have a call to this oracle ALW, and we would like to construct a sparse graph GWC that's going to approximate, that's going to match all the matches between xi and y pi I. And we're going to do that by slowly partitioning the set of intervals. So we're going to start with pi 0, which is a partition that consists of one part, which is all the intervals. And we're going to slowly refine such partition to make them smaller and smaller. Okay, and every time we're going to have roughly lambda to the t part, where lambda is roughly n to the epsilon. Okay, so the goal is we have a partition of size lambda to t minus 1, and we want to build a new partition pi t for lambda to the t parts, and that's going to preserve the matching of the AL distance, right? And we want to do it efficiently. So there is two main parts of our algorithm. The first one, we call it clustering. And the way we're going to do it is we're going to sample a bunch of anchors, right? We're going to sample for every new part in this in partition in pi t. We're going to sample in anchor A. And we're going to compare A to all the other intervals in its partition. And we do that using the AL oracle. This is the place, the only place where we use the AL oracle, in fact. And then we're going to identify all the C matches, all the other intervals that are a distance at more, the AL distance at more C from this anchor A. And we're going to call that the extension of A, and we're going to color it purple, right? So let's see how it works. We sample this interval that is referred to as the letter A here, and we're going to find all the other A's in the partition. And then what we're going to do is, you know, assuming this is not a very large cluster, then we'll talk in a second what we do then. We're going to use, we're going to give credit to each one of those purple A's, every one of those A's that we found. And we're going to have a fixed credit, and we're going to split it among all the A's. And this is the first step. And then the second step is we're going to do partitioning by coloring. What does it mean, partitioning by coloring? Is we're going to take this phi of A that we gave to each one of the intervals J's in the partition, in the cluster, and we're going to further split them to other nearby intervals, right? Proximity intervals. And we're going to generate a score that is called the psi score. And this will be for many more intervals, right? The idea is to color all the intervals. And this is how it works. So after we find all the A's, then we take some radius around those A's, and we're going to color them with the color A, right, for all the intervals in such proximity. So the main takeaway is that the intervals are partitioned according to their proximity. We're going to use such color to generate partition, and the interval was partitioned according to the proximity. And we do that until such cluster is sufficiently large, right? When the cluster is sufficiently large that it can cover at least 1/λ part of the existing part, then we don't need to do any more partitioning. We can simply, this is where we add edges actually to GWC. We simply add an edge from A into all of its extension. So we have now we have these two hopas between every match that is in the partition pi t-1, because we found all the matches, and this means that if this cluster is dense enough, then we can stop partitioning and we can add edges to the graph. So this is the idea in high level. And then the question is, how do we do the partitioning, right? Because an interval can get multiple colors, or it may get no color at all, right? And there is a lot of caveat, but at high level, and let's assume for now we have some comfortable assumption, right? Like ultra triangle inequality assumption that is written below. Then it turns out that we can simply use a weighted mean hash function. We can sample one meanwise hash function h and apply to all the interval. And because the distance between we get the guarantee on the L1 distance between of the coloring between each xi and y pi I, then this will give us a error that is at most a constant from whatever was already corrupted, was already in the wrong partition, let's say, or the cost was more than C. Okay, and this is very nice under the ultra triangle inequality assumption. But if we don't have such assumption, it's actually not so easy. And we could not apply the usual idea to make it work. So instead, we came up with a new idea, which was to smooth out everything. Instead of using the mean hash, we define a new function, which is called the distortion resilience L1, which allow us to distinguish between the multiplicative error that one necessarily gets from using from the different neighborhoods between xi and y pi I, right? Because we're not looking for, we don't assume perfect neighborhoods anymore. We just have regular triangle inequality. So this creates multiplicative approximation, distortion, and we would like to distinguish it from additive errors. And we use this distortion resilience and hence L1 function. And in addition, we still want to have like this very nice equivalence classes, but we cannot anymore because we have this multiplicative error. So what we do is we logically look at every interval as a lot of parts, and every part it's a pair of interval color part, and this we do that instead of use the minwise hash function, and this creates a lot of new challenges that we deal with in our paper. So that's more or less it. I can summarize, one can compute the distance in linear time up to a constant factor. The approximation we get is roughly double exponential in 1 over epsilon.